Hey everybody, Mr. Lee here. Today we're going to go over potential due to point charges and efields. This one we have a couple of things to write down, so get your writing hand ready and let's get started. So the first thing I want to go over is the definition of electric potential energy. Electric potential energy is the energy stored in the E field due to a position of charge. And one way that we can really clarify this is U, which is the variable for potential, or potential energy, is the negative work done by conservative fields to arrange objects in a system. Now, this is just a really fancy way of saying if we have an object that is placed within a field. So for example, if we have a gravitational field, this is something that we've done in mechanics, right? So here's a gravitational field. This is the floor. And let's say we have a red box, right? So we have a red box here. And if I lift up that red box up a height of delta H, okay, so now the height is up here, we can say that this red box now has potential energy. Okay, and so what this means is that if you have an object or if you have a charge and you move it to locations where it doesn't necessarily want to be, now I hate personifying objects or charges like that, but you're going against the field, you're going against nature. What we're doing is you're storing energy within the field itself. And the reason why I say you're storing energy within the field itself is if we go back to this box example, right? If we put the box up here and within the gravitational field, and as soon as we let go, the energy that is stored within the field, that energy would go from potential to kinetic energy. And what I mean by that is the object will fall down, okay, and it'll now have kinetic energy as it falls. The potential turns into kinetic. All right? Okay, so with that out of the way, let's go over a couple of formulas. And as I write these formulas, please note that potential is a scalar quantity. It depends on position and the push and the pull of others, meaning that it doesn't have direction. Okay, so this is just magnitude only, because vectors have magnitude and direction. Okay, so the formulas we have for potential so far is gravitational potential energy. So we have UG is equal to mg delta H. Let me get a finer point pen. There we go. And we also have the gravitational potential energy between two planets of UG times capital G, M1, M2, all divided by R, and this is negative. And we have potential energy of a spring, which is equal to 1/2 kx squared. Okay, these are the three formulas from the mechanics unit, and I'm about to introduce to you the next one. But before I do that, I want to highlight a couple of things. Here, the potential energy, we are within a gravitational field. And it's the object that's causing the gravitational field that's doing the pushing and the pulling, and it is height dependent. And here we also have a gravitational field, but the pushing and the pulling is done by large objects or planets in this case, and for the spring, the pushing and the pulling is done within the spring itself. All right, so this one, the energy is not stored within the field but within the spring. Okay, so with that out of the way, time for your next formula. The potential energy, or the electric potential energy, is equal to Q times V. And we'll dissect that. And another way to write this is K Q1 Q2 over R. All right, so let's break this apart. So what this tells us is if we have a change in voltage, so we can write this as an even delta V, right? So if we have a electric field, so let's say we have, let's do the charge plates. We'll just do, let's say we have a positive charge here. Okay, and we have field lines like so. Okay, so we have field lines like that. Within the field lines, remember, we have equipotential lines, and I'll do this in a different color. Let's do this in red. We have equipotential lines. right? And equipotential lines are just another way of saying what is the voltage at that point. So let's say here the voltage, let's do a finer pen, our voltage is, let's say 10 volts. And out here we can say the voltage is 1 volt. Okay, so if we were to move a charge, a test charge, from position A to position B, okay, we would have a delta V of 9 volts. Now, to bring us back to the idea of potential, okay, when we are within a field, okay, and the field is not the potential lines, but these lines that I drew emanating out from the object itself, right? When we're within a E field and we have a charge within that field, that charge has potential energy. And much like how we started off this entire node session, if we have an object within a gravitational field and we move it within the gravitational field, we're either giving it potential energy or we're taking away potential energy. It's the same for charges. If we have a charge within an E field and we move it from one point to another, okay, we are either giving it potential energy or we are taking away that potential energy. And that potential energy is stored within the field itself. And if we take a look at the formula here, okay, we see that it's KQ1, Q2 over R. What that tells us is, well, it's this exact scenario here, okay, where Q1 can be the charge that is creating the field, okay, or Q2 if you really think about it, because all charges have a field. And if we go from one point to another, we can see how much potential exists at that one point. All right. So if we want to know, are we adding potential or are we taking away potential? The way I like to always think about it is, what does the charge want to do? Okay, so if you go against the wishes of the charges, you are adding potential. If you are doing what the charges wants, you are removing potential. So in this scenario here that I just drew here, okay, let's say we're going from A to B. Now, if this charge was a positive charge, this positive charge does not want to be close to this central charge that we are within the field, okay? And because it doesn't want to be close to it, when we move from A to B, our potential will go down because we are doing what the charge wants to do. If the charge was negative, okay, this negative charge wants to be close to this positive charge. So when we move it away, our potential goes up. A way to think about it is, once again, within the gravitational field. Okay, this object, this red box, wants to be close to the floor. So when we move it away, okay, so if our height increases for the box, okay, our potential energy also increases because we are doing what it doesn't want to do. Okay, it wants to be close to the floor, but if we move it away from the floor, the potential goes up. But if we reduce the height, or if we bring it close to the floor, we are doing what it wants to do. It wants to be close to the floor as possible, so our potential will decrease. So keep that in mind as you go with these problems. Okay, always ask yourself, what is the potential doing, or what is the charge doing? What does the charge want to do? And is that a increase in potential or is that a decrease in potential? Now, another way that you can think about this is, what does that potential turn into? Okay, so for us, potential energy in these scenarios will turn into kinetic energy. So let's do the first scenario here. If we have a positive charge, okay, and we go from A to B, we say that the potential decreases. Meaning, if we were to release the object at point A, it's going to shoot away from this big central charge here. Okay, it's going to shoot it away, and when it shoots it away, the potential energy, it'll decrease as it goes from A to B, because that potential energy turns into kinetic energy. Now, on the flip side, if we take a look at a negative charge, okay, let's say we release a negative charge at point B. If we were to release a negative charge at point B, it wants to go towards this big positive charge there. And so as it gets closer and closer and closer, it's going to speed up. Our kinetic energy is going to increase. And so the further away it is, the more potential it has. Okay, it's not going fast yet. It will go fast. All right. And a way for us to really represent this with our big formula here, let's highlight that. That's very important. It's a very important formula, is if we take a look at a graph. Okay, a couple of relationships that you need to know is what that are in the denominator. So if we have a potential position, or potential energy, of course, it is in joules. Okay, the closer you are, usually, if it's the closer you are, if our x is very, very small, our potential can be very, very big. And as we get further out, it has the inverse effect. So what we get in terms of a graph, is a inverse relationship like so. Now, a scenario for this, it could be like a positive and a positive here, right? So when the two objects are very, very close to each other, x is small, our potential is big. Okay, but if we move that x or move that positive charge away, we can say x is big, potential is small. It's a inverse effect. Now, the opposite is true if we were to have, let me go like that, potential x, right? If we have a positive and a negative charge, like so. Okay, so this would be positive and negative. All right. So that's the end of the notes. With this unit, there's a lot of different problems and situations that we can come across. And so check the next couple of videos where I go over different scenarios and how to really dive into these types of problems. I'll see you next time.